what's known about these untamed infinities. So quantum field theory, well, at least if we do expansions in h bar, that's Planck's constant, then we usually describe quantum field theory through these Feynman diagrams. So these are pictures, but they represent algebra. Say this would be gluons interacting to give quarks and W boson, and this would be a correction, a loop correction. So it's a more complicated contribution. And this is all part of quantum field theory. The more loops you see, the more complicated it gets, and the more quantum-like it gets, the more contributions that go like Planck's constant. Now, gravity, it's similar. You can draw these same pictures. It's just a lot more complicated. Now, the quantum field theory, it's really the most precise theory that we know by a long, long shot. And the favorite example that people like to use about quantum field theory, about its precision, is something called the anomalous magnetic moment of the electron. And what that is, it's the magnetic moment of the electron compared to its spin. And when you compare the theoretical prediction against experimental measurement, it's accurate to 1 part in a billion. Unbelievable. Absolutely unbelievable. The first calculation done by Schwinger, okay, he didn't use Feynman diagrams actually, but anyway, done by Schwinger, and then Kinoshita devoted his life to making these theoretical predictions. Like I say, 1 part in a billion. Extremely complicated calculations. You do it, and it works 1 part in a billion. There's no other theory like that. Now, this is using quantum electrodynamics. This theory I will be talking about will be quantum chromodynamics and its connection to gravity. We call it also Yang-Mills theory. Sometimes use that interchangeably. Okay, and let's see what people said about quantum field theory of gravity. So you've probably read Brian Greene's book or some other popular book, and you see some statements. Einstein's theory of general relativity is incompatible with quantum field theory. Now, the experts in the audience know that that's a little bit of a silly statement, but nevertheless, people say it. But this statement is usually based on another statement, which is more precise. It says, all quantum field theories of gravity have untamed infinities, and that's known as the non-normalizability problem of gravity. Okay. So, where do these statements come from? And then, the more important question, are these statements true? These are statements people repeat, but just because they get repeated doesn't mean that they're true. Now, let's have a look at infinities. What do I mean by infinities? Oh, I literally mean you add something up or do an integral and you get infinity. By the way, if you have an iPhone, don't do this. Don't Google it. 1 plus 2 plus 3 plus 4, don't Google that, because you'll find the answer is minus itself, not infinity. So that'll contradict what I just said. But anyway, it's naively infinity. Actually, it's true. Google it. Now, normally we don't think about sums, but really integrals. And this would be a good example. This is a logarithm. You do this integral, you get infinity. And in quantum field theory, we deal with infinities all the time. Standard practice. So this would be a very typical integral. A more complicated one than that. A very typical integral of quantum field theory. And the answer is infinity. This infinity is actually our friend. It's called a renormalizable theory. We know exactly how to deal with it. Some redefinition of coupling constants, and then the infinities are swept away. They're our friends. Not a problem. But then there are another set of infinities when you get to call them unhappy theories like gravity. And those infinities are not so easy to deal with, and we call them non-renormalizable. And just to give you a little taste, this is David's comment about the technical subject. When you look at a gravity Feynman diagram, so this is actually a very complicated one, but it's actually an interesting one. This would be 1, 2, 3, 4, 5 loops. So that's an interesting one for us. And you look at the integrals that you get, comparing Einstein gravity against Yang-Mills theory, then what you find is the integrals that you have, the more of these are mementa, and then you're integrating over them, more upstairs, and then you find integrals that are very badly behaved. And it's actually connected to the fact that Newton's constant carries dimension, and it's directly connected to the fact that the integrals you find have a very bad behavior as these are meant to go off to infinity. Okay. And that's the non-renormalizability problem. And there's absolutely no doubt about this, that the Feynman diagrams of quantum gravity are poorly behaved. That is, you could say, proven. But you have to worry about something, and this is the loophole, and this is a loophole everybody knows, is that there might be cancellation between the diagrams, but there's something special going on, a hidden cancellation. And when I say hidden cancellation, I don't mean hidden from the theory, I mean hidden from us humans. Like, we can't see it, but there's some cancellation. It's just our description in terms of Feynman diagrams makes it hard to see what's going on. The question is, are we sure there must be bad infinities if you add up all the diagrams? How do people know? Of course, my answer is going to be people don't know, but we'll get to that. Now, we're going to look at a type of theory called supergravity, and that involves this idea of supersymmetry. It's actually kind of a cool word, super. It's actually a technical word. When you use the word super, it means a symmetry between forces and matter, between bosons and fermions. So, and what supergravity is, it takes this idea of supersymmetry and it combines it with gravity. So the idea is that if you have a graviton, then what supersymmetry postulates is that there's a particle called the gravitino, which is a superpartner of the graviton. Now, we're pretty certain that the graviton exists, but not so certain the gravitino exists. But on the other hand, it's just a theoretical toy model to try to understand